You need to share the screen, I think.
Sorry? Sorry, what are you saying?
Sir, you have not started sharing the screen.
No, I'm just asking questions
Okay,
first.
okay, okay. Okay.
I will start sharing. Yeah. So I'm just doing a quick recap of what we did last time before I start sharing the screen. So we showed that alpha wedge d alpha power n minus 1 is also equal to the Riemannian volume form, right, of the unit tangent bundle with the metric induced by the Sasaki metric restricted to the unit tangent bundle, right? Okay.
Yes.
Okay. So now, okay, 1 second. Actually, wait 1 second. I'll just notes. So are there any questions about this so far? Any questions about what we did last time? Okay, all right. So fine. So we have that the geodesic flow preserves the canonical one form alpha. And as a corollary, we got that the Gauss lemma follows as a corollary, right? You remember last time we showed the Gauss lemma follows from the fact that the geodesic flow preserves the contact form, right? In fact, the Gauss lemma is a special case of the fact that the geodesic flow preserves the contact one form, right? Okay. So before we proceed, since I said last time that this alpha wedge d alpha power n minus 1, this is up to a constant. It is the volume measure of T1m, which is also called the Liouville measure on T1m. Okay. And so the geodesic flow preserves the Riemannian volume of T1m. So before we go any further, I want to just say how to calculate integrals with respect to this Riemannian volume measure on T1m. Okay, so T1m has what the structure of what's called a fiber bundle. Okay, so the tangent bundle is what's called a vector bundle, right? Over every point P, you have a vector space TPM. And locally, the tangent bundle is a product, right? So of a vector space with the manifold, with an open set in the manifold. And the unit tangent bundle, it's what's called a fiber bundle. So for each point P, you have over it the unit tangent sphere, T1, TP1M, right? TP1M. And so that is topologically, it's a sphere. And locally, the unit tangent bundle is a product of an open set in M with the sphere Sn minus 1, right? Locally, it's a product. You can write it as a product. So it's in this sense, it's a fiber bundle where the fibers are spheres. Okay, the fibers are spheres. And so the idea is when you integrate on this fiber bundle, you should have a sort of Fubini's happening for the integration. So the integration should be over the base, and then for each point in the base, you integrate over the fiber, which is the unit tangent sphere. Okay, so an integral with respect to this Liouville measure or this Riemannian measure of T1m, we should be able to write it as an iterated integral, integrating over the base m, and then for each point in the base, you integrate over the fiber TP1m. Okay, so I want to show you how to do that. All right, so let me just recall the setup first. So we have our Riemannian manifold M. We have the geodesic vector field G. So if theta equal to PV is a point in Tm, then G theta is the element of T theta Tm with horizontal and vertical components V and 0, right? And alpha is the canonical one form on Tm. So remember, alpha is just Sasaki inner product with the geodesic vector field, right? So alpha theta of a tangent vector xi is Sasaki inner product of G theta with xi. And so this is the same as d pi theta xi with V, inner product d pi theta xi with V, where xi belongs to T theta Tm. So we're looking at the unit tangent bundle. So then we want mod V to be 1. So then theta belongs to T1m. So the tangent space to T1m at theta, last time we saw this is xi in T theta Tm, such that inner product of K theta xi with V is 0, right? Where K theta is the connection map. So this means the vertical component of xi must be perpendicular to V. Okay, so this is telling you basically that the length of the tangent vector should not change. Okay, this is nothing but the derivative of the energy function, which is the norm squared of V. Okay, so this is basically the same as dH theta of xi, where h equal to half norm V squared is the energy function. So you want on T1m, basically h is constant, right? So the tangent space is the kernel of dH. So this is dH, okay? This inner product with K theta xi. Inner product of V with K theta xi. Okay. And then we looked at the kernel of the one form alpha. So alpha is inner product of d pi theta xi with V. So this will be xi in T theta T1m such that d pi theta xi V is 0. So this is a subspace of dimension 2n minus 2 inside T theta T1m. And I want to give you a direct sum decomposition of this into a horizontal part and a vertical part. So for the horizontal part, let's define a subspace of the horizontal space called H tilde theta. So these will be horizontal vectors of the form W comma 0, where W is perpendicular to V. Okay. So these are in H theta, and they will also be in S theta, right? Because well, H theta is a subspace of S theta. So right. Okay. But why am I doing this? So, well, I don't need this intersection S theta. I can just write H theta here. So this is an H theta. And H theta I can write as the span of G theta direct sum, orthogonal direct sum with H tilde theta, right? Yes? Is this clear? Because H theta is all vectors of the form W comma 0, and then W I'm splitting up as a component in the direction of V plus a component in the direction of V perp, right? So the component in the direction of V is a multiple of G theta plus a component in the direction of V perp gives me an element of H tilde, right? So this is an orthogonal direct sum. Is this clear?
Yes, sir.
Okay. Similarly, I want to look at a part of the vertical space. So I look at V tilde theta. So this will be vertical vector 0 W in V theta, such that inner product of W with V is 0. So this will be contained in the vertical space. And this is also in S theta, right? In the kernel of alpha. Oh, actually, wait. 1 second. What am I doing here? Sorry. This should be. Okay. And so V tilde will be vertical vector 0 W with inner product WV equal to 0. So this is contained in V theta. And this is also contained in S theta, right? Because the vertical component W is perpendicular to V. And that is exactly, well, sorry, I mean, this is contained, so this is contained in T theta T1M because the vertical component is perpendicular to V. And it is also contained in S theta because the horizontal component is 0. So this, this equation holds. And then S theta I can write as H tilde theta direct sum V tilde theta. Is this clear? Sorry, so actually, no, this was right. This is in H theta intersect S theta. Because in S theta, I want, no, this was correct actually. I want horizontal vectors which are in the kernel of alpha. So that means the horizontal component should be perpendicular to V, right? D pi theta xi should be perpendicular to V. So that's why I'm looking at W which are perpendicular to V. Right. No, so this was correct. This is H theta intersect S theta. And this is in V theta intersect S theta. And S theta you can see is equal to H tilde theta direct sum, orthogonal direct sum V tilde theta. Is this clear? Yeah, because S theta would be what? It would be xi in T theta T1M such that D pi theta xi V is 0. And T theta T1M means that K theta xi V is 0. So this is the subspace where both the horizontal and vertical components are perpendicular to V, right? That is S theta. So that would clearly be this H tilde direct sum V tilde, right? H tilde is where the vertical component is 0, horizontal is perpendicular to V, and V tilde is where the horizontal component is 0, vertical component is perpendicular to V. So adding these together, you'll get S theta. Is this clear?
Yes.
Okay. So now I can write T theta T1M as I can write it. So each of these has dimension n minus 1. S theta has dimension 2n minus 2. And now T theta T1M, this has dimension 2n minus 1. I can write it as the span of G theta direct sum S theta. Is this clear? Yes, because I mean G theta belongs to T theta T1M and S theta is nothing but G theta perp, right? Inside
Yes, sir, yes.
T theta T1M. S theta is just you look at the definition, it's the kernel of alpha. So alpha is inner product with G theta. So S theta is nothing but G theta perp. So this is just G theta direct sum G theta perp, right? That is S theta. So this is an orthogonal direct sum. And then I can further break this up as R G theta direct sum H tilde theta direct sum V tilde theta. Okay. So these are orthogonal decompositions. Okay. So this is an orthogonal decomposition. And this here is also an orthogonal decomposition. Okay, and maybe I should just note that here, if I look at the almost complex structure on the tangent bundle, then it will interchange these two, right? J theta will interchange these two. Is this clear? Yes, because just W0 will go to 0W, where W is perpendicular to V. Is it clear?
Yes.
Right? Okay. And omega, which is minus D alpha, that restricted to H tilde direct sum V tilde. This is a symplectic form, right? It's alternating and non-degenerate restricted to this S theta. That's what we showed, right? So omega theta. So this was Sasaki inner product of J theta xi with eta, and omega is equal to minus D alpha, we showed, and omega theta restricted to S theta is non-degenerate. Okay. All right. Now, let's come to the computation of the Riemannian volume form, right? So computing with Riemannian volume form d vol T1n of T1n. So how do we calculate integrals with respect to this Riemannian volume form? So I want to say we can do this as an iterated integral. You integrate over the base, and then for each point in the base, you integrate over the fiber, which is the unit sphere, the unit tangent spheres. Okay. So how do we do this? So first of all, how do we compute the Riemannian volume form of n? So if d vol m is equal to the Riemannian volume form of n, let's assume m is orientable, right? It's an oriented manifold. So we can talk about the Riemannian volume form, right? So this takes the value 1 on any positively oriented orthonormal basis for all positively oriented orthonormal basis of TPM. Okay, So how do you compute a integral? So if phi equal to x1 to xn from u in M to V in Rn is a chart, and psi is equal to phi inverse from V in Rn to U in M. And if f is a continuous function with compact support in U, okay, then the integral over M of f dvol M is equal to the integral over U of f dvol M, and this is equal to the integral over V of the pullback of f dvol M by psi, right? So psi star of f dvol M, yes. And so what is this pullback going to be? The integral of this pullback? This will be the integral over V f of psi of x, and then I'm integrating the pullback, so it will be dvol M of psi of E1 to En, where E1 d psi of E1 to d psi of En, where E1 En is the standard basis of Rn. So those will map to del del x1 up to del del xn. So this will be basically dvol M at the point psi of x applied to del del x1 to del del xn, okay, dx1 dxn, right? And now what is this volume form applied to the basis del del x1 to del del xn? Well, this is a top degree form which takes the value 1 on any positively oriented orthonormal basis. So if I take a frame, an orthonormal frame on U, then this will be f of psi x. This dvol of del del x1 to del del xn, this is just the determinant of the map which sends my orthonormal frame, let me call it EI, at the point psi x. This maps to del del xi, right? I goes from 1 to n. Yes, is this clear?
Yes.
So it's just an integral of f times this determinant, okay, where EI is an orthonormal basis of vector fields. on U. Is this clear? Okay. So this is how we compute an integral with respect to the volume form. It's just the integral of the function times a determinant, right? With respect to dx1, dxn on the image in Rn. Is this all right?
Yes, sir.
Okay. Now I want to calculate the integral of a function with respect to the volume form of T1n. Okay, so how do I do that? So now I want to calculate, so let me take theta naught to be a point P naught V naught in T1n. Okay. And let me take EI to be an orthonormal frame in a neighborhood of P naught in N. Okay. And so I take, now I take U tilde to be a neighborhood of theta naught in T1m. So U tilde is a open subset in T1m, which is a small neighborhood of theta naught in T1m. And now I take F to be a function with compact support in U tilde. All right, so I want to compute the integral of F with respect to the volume measure of T1n. Okay, so how do I do this? So first I need coordinates on U tilde, right? So how do I get coordinates on U tilde? I take U to be pi of U tilde. So this is contained in N. This is a neighborhood of P naught in N. And I take phi equal to x1 to xn from U in M to V in Rn, a chart, okay, on U. All right. Now I want coordinates on, so we have coordinates x1 to xn, y1 to yn on tu defined as follows. The yi's are basically the coefficients of a tangent vector with respect to this orthonormal frame EI. Okay, so so how do I write it for so for V in TPM, V is equal to sum over I yi of PV EI of P. All right. Is this clear? Okay. Yes. So then is this all right?
Yes, sir.
Okay. So then y1 to yn restricted to any unit tangent sphere TP1n. This maps TP1n to Sn minus 1, right? Because these are coefficients with respect to an orthonormal basis. So the unit tangent sphere in the tangent space corresponds to the unit sphere in Rn. Is this clear? Yes? Okay. Yes?
Yes, yes.
Yes, sir.
All right. Okay. So now suppose we can assume that suppose y1 to yn of P0 V0 is equal to let's say the North Pole, some, well, it doesn't really matter what it is. So say some vector n, let me just call it n, in Sn minus 1 or capital N, okay. Capital N in Sn minus 1. And I take W tilde is a neighborhood of n in Sn minus 1 such that so for assuming that this U tilde is small enough, so then my unit tangent vectors in U tilde are all close to P0 V0. So their image under y1 to yn will be close to the image of P0 V0. So it will be close to n. So for U tilde small enough, y1 to yn of U tilde this is contained in W tilde. Okay. And I let Z1 tilde to Zn tilde I let these be charts on Sn minus 1 from W tilde in Sn minus 1 to some W in Rn minus 1 So this is an open set. This is open. This is a chart of Sn minus 1. And I let, sorry, this is Zn minus 1 tilde. And I let Z1 to Zn, this is equal to, sorry, Z1 to Zn minus 1 equal to Z1 tilde to Zn minus 1 tilde composed with Y1 to Yn. So this will map U tilde to W in Rn minus 1. Okay. So then I get charts. Let me call it capital Phi equal to x1 to xn, z1 to zn minus 1. These are charts on U tilde, right? So this will go from U tilde to V cross W in R